We're going to talk about using Taylor series to help figure out whether a fixed point is attracting or repelling. Come on, have a seat. Okay, so let's get serious. Today we're going to talk about using Taylor polynomials to figure out the behavior of a fixed point when the derivative is 1 at that fixed point. So the example we'll use is the sine function, and let's get started. Suppose we have the DDS xn plus 1 equals f of, equals sine of x n. So in this case, the function that we're looking at that governs the DDS is the sine function. Now, if we look for fixed points, we notice that since the sine of 0 is equal to 0, this means that x equals 0 is a fixed point of this DDS. Then we want to see whether the fixed point is attracting or repelling, because that tells us what happens in the long run. So we look at the derivative, f prime at 0, and we notice that's cosine of 0, which is 1. And if you remember, 1 is indeterminate. It doesn't tell us whether it's attracting or repelling. If the derivative at the fixed point was bigger than 1, then we would have a repelling fixed point. And if the derivative at the fixed point was less than 1 in absolute value, we would have an attracting fixed point. But when it's equal to 1, we don't know. So what we're going to do is use the Taylor polynomial, which looks like the sine function close to 0, to help us figure this out. Now, we figured out the Taylor polynomial of sine function before, so I won't do that here. The Taylor polynomial, the third degree Taylor polynomial of the sine function was x minus x cubed over 6. So how can we use that information to help us figure out what the behavior of this DDS is near the fixed point at 0? Well, let's draw a picture. And in our picture, we'll put the line y equals x, with this diagonal red line. And now let's look at the graph of the third degree Taylor polynomial near 0. There are two cases to consider. When x is bigger than 0, x cubed over 6 is bigger than 0. And so that tells me that the graph of P3 is going to be below the line y equals x when x is positive. Somewhere down like that. And when x is negative, well, in that case, x cubed over 6 is actually negative, less than 0. And since we're subtracting that from x, that tells me that x minus x cubed over 6 will be above the line y equals x, close to 0 on the negative side. This picture is very helpful because it tells us that when x is positive and close to 0, because the graph of the Taylor polynomial is underneath the line y equals x, the orbits will move to the left. And on this side, where x is negative, because the graph of the Taylor polynomial is above the line y equals x, the orbits will move to the right. And this tells us, in the end, that x equals 0 is an attracting fixed point.